Free predicate logic is a family of logical systems that modify classical predicate logic by relaxing one of its central assumptions, that all singular terms refer to existing objects in the domain of discourse. In classical predicate logic, every constant and every value of a variable is assumed to denote an object in a non-empty domain of existing things. Free predicate logic rejects or weakens this assumption, allowing for non-denoting or empty singular terms or terms that refer to non-existing entities. The term free reflects the idea that quantifiers and constants are no longer tied to an implicit ontology that guarantees existence. As a result, free predicate logic provides a flexible framework for reasoning about empty names, non-existing objects, fictional entities, future objects, possible but non-actual things, abstract objects, failed descriptions, etc. Several philosophical and practical motivations have been offered for free predicate logic. One major motivation arises from natural language. Ordinary discourse frequently contains names and descriptions that seem to fail to refer to existing things, such as Pegasus, the present King of France, or the greatest integer. Classical predicate logic struggles to accommodate such expressions without distortion. A second motivation comes from philosophical logic and metaphysics. Classical logic appears to commit us to the existence of any object that can be named or quantified over, which some philosophers regard as an unwarranted ontological commitment. Free predicate logic allows us to separate questions of reference from questions of existence. Finally, free predicate logic has applications in, for example, computer science, database theory, modal logic, and temporal logic, where it is often useful to reason about objects that may not yet exist, no longer exist, or exist only in certain states or contexts. The key difference between free predicate logic and classical predicate logic lies in their treatment of singular terms and quantifiers. In classical predicate logic, every singular term denotes an object that exists. Universal and existential quantification presuppose a non-empty domain of existing things, and atomic formulas containing singular terms are always either true or false. In free predicate logic, by contrast, singular terms may fail to denote existing objects. Existential claims do not automatically follow from the use of names. Atomic formulas involving terms that do not denote existing things may be true, false, or truth-value deficient, depending on the system. The domain of existing things may be empty. As a consequence, some classical inference patterns, especially those involving existential generalization, are often restricted or invalid in free predicate logic. Free predicate logic is not a single system but a family of related systems. A standard distinction is drawn between positive, negative, and neutral free predicate logic. In negative free predicate logic, atomic formulas containing terms that do not denote existing things are taken to be false. For example, if Pegasus does not denote an existing object, then Pegasus is a winged horse is false according to this approach. Only existing things have properties. In positive free predicate logic, some atomic formulas involving terms that do not denote existing things may be treated as true. According to this option, John is thinking about Pegasus can be true, even if Pegasus does not denote an existing object. Individual constants can refer to non-existing things, and non-existing things can have properties according to this view. These approaches preserve bivalence. In neutral free predicate logic, atomic formulas involving non-denoting terms are neither true nor false. Instead, they lack a truth value. This approach often leads to a non-classical semantics, such as a three-valued or partial logic, and is particularly attractive to those who wish to model presupposition failure in natural language. The syntax of free predicate logic is largely the same as that of classical predicate logic. We have individual constants and variables, predicate symbols of various arities, logical connectives and quantifiers, etc. In addition, many systems introduce an explicit existence predicate, E. Sentences asserting existence are then expressed directly, rather than being built into the logic of quantification. Thus, while the formal language remains familiar, its interpretation is crucially different. Semantically, free predicate logic modifies classical model theory. A model often includes two domains, one inner and one outer, where the inner domain is a subset of the outer domain. Inner domains contain everything that exists and may be empty. Outer domains include every possible object and are usually taken to be non-empty. In some systems, an interpretation function assigns every constant in the language a member in the outer domain. In such systems, constants can denote non-existing things, but there are no non-denoting constants. In other systems, interpretation functions for constants may be partial rather than total. That is, in such systems, a constant may fail to denote any object whatsoever. Truth conditions for quantified sentences are adjusted accordingly. For example, an existential statement, "There exists an X such that Px is true," only if there is an object in the inner domain, that is, that exists, that satisfies P. In many free systems, we cannot derive "there exists an X such that Px" from Pa. Universal statements are often treated as vacuously true when the domain is empty, though some systems reject this. Different semantic frameworks are used, including classical two-valued semantics, partial semantics, and many-valued semantics. Despite these differences, many central logical notions can be defined in free predicate logic much as they are in classical logic. A sentence is logically true if and only if it is true in all models of the relevant kind, logically false if and only if it is false in all models, and logically contingent if and only if it is true in some models and false in others. Logical consequence and argument validity are often defined in terms of truth preservation. A conclusion follows from a set of premises if and only if there is no model in which the premises are true and the conclusion false. These definitions must be adapted to accommodate empty domains or partial interpretations, but the overall structure remains familiar. Several proof systems have been developed for free predicate logic. These include modified natural deduction systems, sequent calculi, semantic tableau systems, and axiomatic systems. The main differences from classical proof systems involve restrictions on existential generalization and the introduction of explicit existence assumptions. Free predicate logic can be fruitfully combined with other logical frameworks. In modal logic, it allows for reasoning about possible but non-existent individuals. In temporal logic, it supports reasoning about objects that come into existence or pass out of existence over time. It can also be integrated with, for example, epistemic, doxastic, and deontic logics. Many systems of free predicate logic enjoy familiar metalogical properties, such as soundness and completeness, with respect to their intended semantics. However, the presence of empty domains or non-denoting terms can affect some metalogical properties depending on the system. Free predicate logic is generally a conservative extension of classical logic, meaning that classical results are preserved when existence assumptions are restored. Free predicate logic provides an intriguing and flexible alternative to classical predicate logic, especially for reasoning about non-existence, reference failure, and ontological neutrality. By separating logical form from existential commitment, it offers a framework that seems to be closer to natural language and more adaptable to many philosophical and technical applications. Whether viewed as a correction to classical logic or as a complementary tool, free predicate logic occupies an important place in contemporary logical theory.